In this video, I'm going to show you how to calculate velocity using differentiation. Here we've got a problem of a moving particle, and we're told that the position of the particle moving along the x-axis is given by this function x of t equals t squared, where x of t represents the x-coordinate of the particle, which is measured in meters, and t represents the elapsed time, which is measured in seconds. And we want to calculate the velocity, v of t, of the particle. So we've got a position function, and we want to calculate the velocity using that position function. First of all, though, let's talk about what this position function is actually telling us. Here we've got a table of some values for t and some values of the position function. 0 squared is just 0, 1 squared is just 1, 2 squared is just 4, and 3 squared is just 9. What this tells us is that at t equals 0, when the particle first starts out, it's at an x-coordinate of 0, so right here. And then at t equals 1, the particle has moved to the x-coordinate of 1. Then at t equals 2, the particle has moved to the x-coordinate of 4. And then at t equals 3, the particle has moved to the x-coordinate of 9. So the particle is moving to the right towards the positive side of the x-axis, and it's moving further and further each second of travel. So now that we know what the situation looks like, how do we actually calculate this velocity of the particle? Well, remember that for constant velocity, you can just compute it by taking the displacement and dividing it by the duration of time. But in this problem, we don't have a constant velocity. If we tried the constant velocity formula on the interval as t ranges from 0 to 1, we get a displacement of 1 divided by a duration of 1, so velocity would be just 1. But if we tried it on the next interval, we'd get a displacement of 3, 4 minus 1 is 3, and then still divided by 1, so velocity is 3. So the velocity is it's really changing at every moment in time as the particle is moving. So how do we deal with that? Well, how we deal with that is we just take the limit of this constant velocity expression as the change in time goes to 0. This constant velocity just tells us the average velocity over a time interval, and if we shrink that time interval to 0, then it's like we're finding the velocity at a particular point. And this limit, as delta t goes to 0, well, that's just infinitesimal. That's just dx dt. So velocity is just the derivative of position function with respect to t. So let's go ahead and compute this for our problem at hand. So v is just the derivative d over dt of our position function. And our position function is just t squared. So put that t squared into the derivative and take that derivative of t squared, and you get v equals 2t. So velocity is just 2t. We can evaluate the velocity at each moment in time. At t equals 0, you plug in 0 here, you get 2 times 0 is 0. At t equals 1, you plug in 1 here, you get 2 times 1 is 2. Then plug in t equals 2, 2 times 2 is 4. And then 2 times 3 for t, that's 6 for velocity. The results here also make a lot of sense in the context of our problem. Initially, the particle is traveling to the right a little bit, and that matches a kind of small velocity, 0 to 2, but then it's traveling faster and faster towards the right. It starts covering more distance in the same amount of time, and we see that the velocity is starting to increase. And it increases more and more. It goes 2 to 4 to 6. So great, it matches up. Our result makes a lot of sense. The last thing to discuss for this problem is what are the units of velocity? The units of time are just seconds. We're told that in the problem. T is the elapsed time in seconds. The units of x, those are meters, measured in meters. What about velocity? What are the units of velocity? Well, velocity consists of dividing the position by the time, so that's dividing meters by seconds, so velocity units are just meters per seconds. So what these velocity measurements mean in terms of physical quantities, it means 0 meters per second, 2 meters per second, 4 meters per second, 6 meters per second. Here's another example, which is similar, but this time we've got a more complicated position function, and we want to figure out more things about the traveling particle. So not just its velocity, but also when does it change direction, and also what is its speed at this particular time, t equals 3. Let's take things one step at a time though. So like before, let's just take a look at the position function, get some visual interpretation of what that means in terms of the traveling particle. So here we've got a table, so t equals 0, 1, 2, 3, and the position function evaluated at those moments in time, and we can plot that on our x-axis. So the particle is starting out at t equals 0, it's at an x-coordinate of 5, then at t equals 1, it's at an x-coordinate of 6, so it's moved a bit to the right, but then at t equals 2, it's at an x-coordinate of 3, so it's darted to the left a little bit. And at t equals 3, it continues darting to the left. Now it's at the x-coordinate of -4. So it's reached the origin and it's completely passed it up and kept going over to the left. Alright, so now that we have a picture of what's going on here, let's go ahead and compute our velocity of the particle. So from before, we know that the velocity is just the derivative of position, so we can go ahead and evaluate that. That's d over dt of our position function. So let's write that in. Our position function is -2t squared plus 3t plus 5, and we can differentiate each of these terms individually. Derivative of -2t squared, just bring down the 2, and you've got -2 times 2t, which is, that's just -4t, and then derivative of 3t is just the coefficient, which is 3, so -4t plus 3, and derivative of a constant, 5, that's just 0, so it just goes away. So this right here is our velocity function. V of t is just -4t plus 3. And now before we go on to the next parts, let's take a second to make sure that this function makes sense in the context of our problem. Let's evaluate it at some points. At t equals 0, the velocity, you just plug in 0 here and you get 0 plus 3 is 3. At t equals 1, you plug in 1 here, so -4 plus 3 is just -1. At t equals 2, velocity is -4 times 2 is -8, then plus 3, that's -5. And then at t equals 3, that's -4 times 3, which is -12, then plus 3 is -9. Alright, so let's look at these velocities in the context of our problem. So initially, at t equals 0, the particle has positive velocity, and that means it's moving to the positive side of the x-axis. And that makes sense because at t equals 0, the position is 5, and then at t equals 1, the position is 6. So it's moved to the positive, in the positive direction of x. But then at t equals 1, its velocity is -1. So that means that it's moving in the negative direction of x. So from t equals 1 to t equals 2, the particle is moving the other way. Alright. Now at t equals 2, it continues moving the other way. The velocity is still negative, so still moving in the negative direction of x, and it follows that way up to t equals 3 and even afterwards too. So we can tell on our parabola right here, the particle is increasing its position a bit. It has positive velocity at first, and then it turns around at some point where its velocity is 0, and that has to be sometime between t equals 0 and t equals 1, and then it's coming back the other way. It's going to the left, and it reaches the origin and then totally passes it up. So now we're ready for part B. For part B, we want to find when does the particle change direction. Well, it changes direction when its velocity is 0 meters per second, and that's like right about at the peak of the parabola, so right about here, somewhere between time equals 0 and time equals 1 second. That makes sense from our diagram too, because at 1 second we know that it's traveling towards the left, and at 0 seconds it's traveling towards the right. So sometime in between those seconds, 0 seconds and 1 seconds, it has to make that transition to stopping and then going towards the left. So let's solve for where velocity is 0 to figure out at what time this occurs. Say 0 equals our velocity equals negative 4t plus 3. And then to solve this, we'll just add 4t to both sides. So 4t equals 3. And then divide by 4. So t equals 3/4. And yeah, that makes sense. That's between 0 and 1. It's closer to 1, which makes sense because velocity of -1 is closer to 0 than velocity of 3 is. Great, so t equals -3/4 of a second. That's when the particle changes direction and heads in the negative direction. The last part of this problem is to compute the speed of the particle at t equals 3. Well, what is speed? Speed is just how fast the particle is going, but doesn't velocity tell us that? So how to think about speed and velocity is really a vector. It gives us not only how fast the particle is going, but it also tells us what direction the particle is going. Positive velocity means that it's going in the positive direction of x, whereas negative velocity means that it's going in the negative direction of x. With speed, we don't care about the direction of travel of the particle. We just care about how fast it's going. So speed is actually just the absolute value of velocity. We just care about the magnitude of the velocity, not the sign of the velocity. So, okay, so let's find this. At t equals 3, so speed at t equals 3, that's the absolute value of velocity at t equals 3. And velocity at t equals 3 is, well, we've got it right here. Velocity at t equals 3 is just -9. And we want to take the absolute value of that because we're only interested in the magnitude of this. So that's just +9. Absolute value of -9 is just +9. So the speed is 9 meters per second. That's how fast the particle is traveling at time t equals 3 seconds. In the future, we'll also learn how to calculate the acceleration of a moving particle. Just as velocity tells us the rate of change of a particle's position, acceleration tells us the rate of change of a particle's velocity.